And basically, Devaret used to be like a former maintainer of QDF while he worked at NVIDIA. But like these days, he works at a company called Voltron, which is building like a GPU native query engine. So if you're interested in how to do like data processing on GPUs, I'm hoping like this is going to be really the talk for you. So thank you so much, and Devaret, please start whenever you're ready.
Okay, so hi, I am Devrat. I currently am a senior software engineer at Voltron Data, and we make a really nice accelerator native query engine, compute engine. And formerly, I used to work at NVIDIA. As Mark said, I used to be a maintainer of QDF. So today I'm going to be speaking on data analytics on GPU. So I'll first go over the kind of motivation for data analytics, doing data analytics on the GPU, and that would include showing a little bit of a glimpse on how much faster data analytics can be if we do it on the GPU, and then to walk through basically uh, a kind of a use case of how basically to walk you through how to build one from starting from QDF up to Theseus. I'll use a toy workload, and I think this is something many of you might already be aware of. It's called a 1 billion row challenge. I know some people in this Discord channel have also attempted this, and then I'll segue into QDF's group by implementation, which is what we'll use in the toy workload, and then we'll scale that up using TCS, which is our engine. So a quick refresher on what is data analytics. So in data analytics, the data which we work on is almost always in the form of a table, and the table can have okay, it's almost always in the form of a table, and tables are made up of individual columns, and these columns can have different data types, and these data types can be fixed width or variable width. They can be float in date, strings, and even nested types like lists and structs. um, the thing about the table, what brings all these columns together is that values from each of these columns correspond to a single row, and because of, because of that, each column has the same number of values in it, um, which is as many rows there are in the table. If there isn't a value in the column at any place, it can be null. And so you would query when you have one or more tables like these, you would basically ask questions of the data, which would give you some insight. For example, on the right, you see a SQL query. It's not related to this table, but on the right, you see a sample SQL query taken from a popular um, data OLAP benchmark called TPC Edge, and that this in this one you're basically asking for um, customers who have had have done high value orders or something. Okay, so let's first start with explaining what QDF is. It's a GPU accelerated data frame library. So if you're familiar with pandas, the Python library pandas, it's quite similar. So you could even imagine QDF as sort of a GPU backed pandas compatible data frame library. And the benefit of using QDF instead of pandas, if you have a GPU, if you have an NVIDIA GPU on your laptop, you basically almost always going to benefit from using QDF. And the guys at Rapids at NVIDIA have a blog about it, how it's for certain workloads, it's 150 times faster than pandas. QDF, just like pandas, is built with the Python front end, and but unlike pandas, it's built with the CUDA backend. It provides data frame APIs like loading from a file, like reading a CSV file or a Parquet file, and then dicing the data, manipulating it, like filtering some things out, grouping, aggregating, finding the min and max, whatnot, and then even and so the thing with cuDF is it's designed to run only on a single GPU. So if you load a file using cuDF, it's going to load that file onto one GPU, and then on the very same GPU, you're going to be running all other subsequent operations on it. And this is where Theseus comes in. So Theseus is a compute engine, and what that means is that it has backends like cuDF. It can have other backends as well, and it uses cuDF to sort of take a query that you give it. For example, the SQL query I just showed you in a previous slide. It can break it up into small pieces that it knows it can query. It can use cuDF to run, and then sort of merge. Is that a hand raise I hear?
Oh, that's probably Zoom. So like that beeping sound is Zoom. I'll just interrupt you if there's like a critical mass of questions or like any hands raised. So don't worry about too much about this. Although now that you bring it up, folks, if you have any questions, like feel free to raise your hand in Zoom and I'll unmute you. Otherwise, in Discord, there's a lecture Q&A channel. So feel free to ask your questions there and I'll just sort of aggregate them and pause the video when there's a critical mass. I guess I had a first question, which was like, it's sort of interesting to me that like doing data processing on a GPU is kind of like an interesting use case, because I would imagine that like, let's say you're loading a data set and let's say, you know, your data set is less than 40 gigs, so it can fit on a single GPU. You would be asking like multiple sort of similar, like you'd be asking like essentially multiple questions over the same data sets. And so does like cuDF have like an aspect to basically persist a data set on a GPU while you're making queries against it? Or are you basically per query reloading the data set?
Oh no, so cuDF will persist. So what that means is that if you basically start by creating a data frame, and with that you generally read from a file like a Parquet file or CSV file or a JSON file, and then that data frame stays on your GPU. And if you want to manipulate it, the data frame is immutable. So if you do anything with it, it's going to create a new data frame out of it. And if your result goes out of scope, that one gets freed from the GPU. And so you need to think that if there's enough space to hold the new results as well as the old data frame at the same time, plus there's also some operation memory operating bytes needed on the GPU for any kind of operation.
Excellent. So so there's actually another question from the audience. So Kashima was asking, and they're saying, hey, Dave, like I'm a contributor to libcuDF, and one thing I did wonder about, though, especially the Avro, JSON, etc., is there any benchmarks comparing it to CPU parallelized operations? I recall there is work being done to refactor the CSV reader, and I'd like to say it did include benchmarks versus CPU-based implementation. I think it was called ParPaRaw parser.
Oh, yeah. So ParPaRaw parser basically was a project by an engineer, a colleague of mine at NVIDIA. It was his PhD thesis or something. And then, no, just a paper maybe. And it had an entirely different view of parsing the kind of data that you would find in CSV or JSON using scans. I am not qualified to speak on it because I left NVIDIA around the time it was being implemented. But about the benchmarks, I think you would need to ask NVIDIA folks for benchmark. I'm not sure if I'm allowed to speak on their behalf anymore about how much faster the CSV reader is. Personally, I know it's quite fast. I've seen some results somewhere being compared to the Pandas CSV reader, and it was quite fast. Does that answer all the questions?
Yeah, I think so. I see Kashimo typing again, but maybe we can keep going and then we'll sort of.
So if you want to see Parpara in action, I think the JSON reader has already been converted. So you could look at the old JSON reader and the new one and understand how that was implemented. Okay. All right. So I'll continue. So Theseus will use QDF and other backends. Where was I? All right. Yeah, it would break up the computation and it would see how much of it would break it up into tasks and see how much fits on a particular GPU. If there are multiple GPUs on the same machine, it's going to break it up and put it onto different GPUs, and then basically it's going to divide up the tasks between those GPUs and figure out a pipeline so that in the end you get the answer you want. So if it's not a straight group by, if it involves multiple group bys and joins and whatnot, it's going to insert it there and stuff. It can scale not just to a single node with multiple GPUs, but to an entire cluster. And because of that, it's able to work on terabytes and terabytes of data sitting across multiple files across the whole node, whole cluster. Okay, so obligatory slide about data analytics as it is done today. So Spark is the most common data analytics tool, and it's entirely CPU based. If you remember, a couple of slides ago I mentioned about a TPC query. So that TPC benchmark is basically a set of 22 different SQL queries, and you can generate it for 10 terabytes, 100 terabytes, and stuff. And you basically test the performance of the system with it. And what this graph shows us is that if you want to analyze 10 terabytes of data of TPCH generated data using TPCH queries, all of them, then the total runtime asymptotes towards several minutes, and you can't keep throwing money at the problem to make it go any faster. So if you want to make it go faster, you have no option but to switch approaches and go to GPU. And just for an example, if you do it with Theseus, the Spark 10 terabyte line is over here. The Theseus 10 terabyte is way down here. So it's not just faster; it's also cost effective. This has been carried out with 10 DGX servers, so 80 GPUs in total. The files were not CSV, they were Parquet files. Same for Spark. The file system was a remote. There's spilling involved. Not all of the data does fit onto the GPU. There was no tricks involved to make Theseus go faster by pre-sorting the data or pre-caching it or warming it up with cold queries or with hot queries or something. So so I move on to the toy workload. So the 1 billion row challenge, it says that you have a file which contains a billion rows and a billion lines, and each line contains two values, a city and a temperature. And the city is the number of cities is limited. So for a particular city, there are a lot of recorded temperature values, and you need to go. The task is to find the per city minimum temperature, maximum temperature, and the average across those billion lines. So so Mark shared a solution with me by a community member on this Discord channel, and that solution blog was described a custom solution to this, like writing their own kernel. So the solution that solution goes: you first construct an array of all possible cities. So this is like they do mention that it's a small cheat because it's not part of the challenge, but on the GPU you cannot, once you start running the kernel, you cannot allocate more global memory. So assuming this is just an assumption, you just make a list of all the cities first and sort them and place them on the GPU first. Then you construct a similar sized array of per city min, max, sum, and count, and then you use the CPU to put markers to basically go through the file, and after every a bunch of kilobytes, start looking for the nearest line marker and store all of those pointers so that your GPU can start so that you can create some parallelism for your GPU. And so when the kernel starts, each thread in the block will start from one particular pointer into the file data. It's going to read the city, it's going to read the temperature and store them into local variables. And then at the end of the line, it's going to binary search this city into the array of cities stored. And once that particular city is found, it's going to go to the corresponding index of value of the aggregate values and use atomics to aggregate the value over there. So this is being a tailor-made kernel. It has quite a lot of advantages. Like it needs to only go through the data once. It knows that it only has to keep two values in memory, so it doesn't need to go and store it back into global memory. It can just keep it in thread local storage. So yeah, obviously it's not meant to be extended to a general solution. So the blog mentions it runs in 16 seconds on a different V100 GPU. The GPU that's available to me is the A100, and this solution runs in 13 seconds, which is not quite bad. But if we're building a library for data analytics, we need to think of the general solution for this. And in general, there's no guarantee that for there to be exactly one value to aggregate. You could have, apart from temperature, you could have precipitation and wind speed, and you could have multiple key values because it's not necessary that you only group by a city. You could also group by state and city. And as I mentioned to Mark earlier, that there may be multiple passes over the data required, and going through a streaming solution like this doesn't take care of that. So the general solution for this is to first read a CSV file and parse it and store it into GPU memory, and then call a group by on it. So the cuDF solution to this would be simply, as I said, just read a CSV using the CSV Reader API, and then group by based on the keys, and then aggregate the columns. A caveat here is that cuDF cannot, first of all, this is a lot of memory data to be read at once into the GPU, but also cuDF has a limitation of the column sizes being int32 max, limited to int32 max. So it cannot have more than 2 to the power 31 values, which means you can't pull the entire table into the GPU into a single cuDF data frame anyway. So this will read any number of columns you have. It doesn't really worry about what's the key and what's the value. This one is going to group by any number of key columns you give it, and any number of aggregations on any number of value columns. So before I go into the implementation of group by, I'll first need to explain what the cuDF table looks like. So cuDF table consists obviously of multiple columns, and a column consists of buffers, data buffers. So a column, depending on the data type it's storing and whether or not the column does contain null values or not, it can hold multiple data buffers in it. So column 1, for example, has only one data buffer. So I'm saying, so this must be a fixed width data type with no nullability. So all of them are valid values. This one has a data buffer and a null mask buffer, which means some values in the data buffer might be null, and the corresponding bits in the null mask buffer will then be 0. And then there is a view type of the table. So just like the table. The table type, there's a table view type which contains column view types. And the difference between this is that the column type owns the data buffer. So this is like a struct that contains a vector, which is sort of like an RAI object that deallocs upon destruction. This only contains a pointer to that data buffer. Similarly, for the column 2, you only have pointers to the buffer. So the benefit of the table view is that it's cheap to copy around and pass around. So as in the previous slide, when you call the CSV reader, it will give you a table. But when you want to pass something to the group by, you pass it the table view, because as I said earlier, the table is immutable. So you just pass it the view. The view is also immutable. This is like a const pointer to the data buffer. And then the aggregate, and then the group by also returns you another table, another new table. Then I would like to explain.
So sorry to interrupt you, Dave. Like I had a question, like as soon as you said the word view, I started to think about like strides. And so I'm like wondering, like, is this like another aspect of like using these views, which is to sort of either do like reshapes on the data or like changing the order of columns? Like, is this kind of stuff like why the point?
You can change the order of columns, but this is not really used for strides, as in the, if I understand correctly, strides in the kernel sense.
Yeah.
Yeah, no, not for that, but you can, so for example, if you had a CSV with multiple columns in it and you were only interested in 2 of them, you would create a new table view out of 2 column views from that table. And then you can pass that to the group by.
Got it. Okay, makes sense. Thank you.
Okay. So now I would like to explain how the cuDF group by works. I want to preface it with the statement that I'm not the original author of cuDF group by or the various tools I'm about to explain. I just contributed to them, and I just want to share how they work. So first of all, the group by is a hash-based group by. Unlike so it doesn't require any binary search into anything. We need a hash map that can work with CUDA. So with CUDA, you need a hash map that can. So cuDF has its own hash map implementation that for which you need to pre-allocate all storage beforehand. And again, that's because you don't want to go exit from your kernel, go and increase the storage and come back. So the way to do it is you make a hash map as big as the number of possible values that you're going to put in it. So to insert a key value pair into that hash map, you take a key and hash it, and then you take the size of the hash map. Actually, you don't have to do that, but this is how the insert API on that hash map works, is that it will hash the key, it will modulo it by the size of the hash map, and try to store the key in there, the key value pair in there. If the slot is empty, and you know it's empty because the storage is also initialized with a sentinel value. So you do an atomic compare and swap to see if the original value is equal to the value that's supposed to represent empty. And if it's empty, you just paste it in. Actually, you don't need to paste it in. The compare and swap does it for you. If you try to insert a key again, the hash map will do nothing and just return to you the iterator to the place where that key already exists in the hash map. And if there is a hash collision, as there always are, the hash map will try to find the next available slot that's free and then store it there. So that's the hash map. So now we try to insert our keys into this hash map. There's a problem. The keys are variable width. So you don't know how much of storage to allocate for the hash map because keys don't have to be fixed width. Strings, and if you think, okay, fine, I know there are strings, but they're all cities, and I know the maximum size of a city can be that one strange town in Wales is which has a really long name. But then you need lots and lots of pre-allocated storage because the entire hash map, each of the slots need to be as big as the largest key that can fit into it. So now there's a second problem. You can have multiple values as keys, as I already said. So there's in this case there are two columns that make up a key. How do you insert that? You can't plan ahead for that. So the solution to this is that we need to find a way to know the equivalence of rows just by the index of the rows. And to do that, we make a comparator object. So this is a row comparator. It takes the table device view, and this is similar to the table view, except in case of a table device view, all the pointers to all the data buffers in the column are first copied into a temporary, copied into a buffer onto the GPU, and then made a view out of it. So that once you have this stable object on the device, you can query it for give me the ith element of the jth column, and it can give it to you. So once you have that struct, you make a call operator on it, and that's a device function. So this function is going to be called by the hash map. So when you're trying to insert into the hash map, you don't insert the keys themselves. You make the hash map with this comparator object, and then you try to insert indices from this table. In this case, let's say we're trying to see whether the index 0 is the same as the row at index 1. So what it's going to do is it's first going to take the first column of the table. It's going to see it's going to compare the column, and if it's not equivalent, just jump out. If it's trying to, if the first column does compare, the loop will go again to the second column. If it fails at the second column, the comparison fails at the second column, it's going to jump out. And only once I've exhausted through all the columns of the table, and they've all come out equal, do we say, yeah, these two rows are equal. A hash table also needs a hash operator, which is much simpler to explain now that I have explained the equality operator. So the hasher is quite similar to the equality one. Again, takes a table device view. This time you just give it one index and you say, hash the row at index this for me. So it's going to just start with a seed, go through values at that index for each column, hash it, combine it with the previous one, and then go on and go on. So effectively what it's doing is it's going to hash the column 1 value, combine it with the seed value, then hash this column 2 value, combine it with this value, hash column 3, and so on and so forth with all the columns. Eventually you get a hash value to use with the hash table. So you construct your hash table with a custom equality operator and a custom hash operator. So now we put these tools together to build the group by. First, make our hash table again with the same amount of storage as there are the number of rows that we're working with. We also make arrays for output, which are also equal to the number of input rows, because we don't know ahead of time how many unique rows there are going to be. Then we insert the index of the row. It's going to use the operators that we just described to insert them into the hash map, and each insert operator is going to return you the location, an iterator to the place it either inserted or found a pre-existing key. Now, don't worry about the value column of the hash map. Use the value that you got from, you use the iterator that you got from the insert, use it to find the index of this into the aggregate values. So if, for example, row 0 hashed into this place, we know where it is in the whole array of slots. And at the corresponding array, we're going to do our aggregates. And the aggregates are, again, simple atomic operations for min, max, and sum. Eventually, you put in all your values and you end up with sparse data. Now you can basically use thrust to shrink that sparse data. You use thrust to figure out all of the empties in the hash map slots and remove it, so you can use a copy if. And then you also use the same kind of shrinking on the aggregate values. Now you have another problem. We have all the aggregate values for all the unique keys, but they are all in a different order. Now we need to also return the keys that correspond to the aggregate values. And for that, we need a gather operation. So here's our original table, and here is our hash map storage. Now, because we used it in a way where we inserted the same value, we basically don't care about the values part of the hash map. Let go of it. Use just the keys to index into the original keys table and pull out the keys corresponding to that location. So this operation is called a gather, and it's defined for each of the data type that GoodEF supports. So what this means is that you don't have to worry about copying strings and rearranging them from one place to a different in your gather implementation. You can just write gather for strings once and use it in all GoodEF APIs. And even another good thing about the string thing is that there's a specialized implementation for strings gather. If your strings are large, it uses blocks to copy them. Otherwise, it uses threads to copy them, stuff like that. So
it's pretty interesting. Like, I mean, this is kind of reminding me of like a word-based tokenizer. So I'm wondering if you've seen like sort of any intersection between these ideas, because like in like a lot of like traditional ML applications, you might like tokenize like characters or like bytes of a word to sort of like map strings to integers. But like it's interesting that, but the reason why you do that there is that just because in the case of like machine learning, like it doesn't know what like a model doesn't know what a string is, so like you have like some integer to map to it. But here it's interesting that you're doing it to save space instead, because yeah, indeed, strings I think take up a lot of space. Like.
Yeah, actually, what's happening here is that we found all the unique strings while doing a group by. We just basically pulling them out to return, because the values that we had corresponding to those strings were in a particular order, and we wanted them to also be in that order. So yeah, the group by will on each call to aggregate will return the keys table as well as the aggregate values table. It needs to return the keys table every time because it's a new hash table every time, and because of that, your keys can be shuffled around. All right, so the benefit to building your has a cousin for row ordering comparator, so a less than operator, and that one is used for sorting. So the way sorting works in QueryF is also similar. You give it a table view, you give it a row comparator, and you ask it to reorder indices. And because Thrust knows how to reorder fixed width, indices are fixed width, it will give you a sorted order. It will rearrange those indices in the order that they should appear in the sorting of the original table. And then you can again use the original table and the sorted order to gather and rearrange it into your solution, into your sorted solution. The hash map is also used in equality joins, which is hash based. And it's also used for something called dictionary encoding, which is when you have a column which doesn't have a lot of cardinality, you want to save space. So instead of having one data buffer, you have two data buffers. One of them contains the actual unique values. The other one contains indices into these values. And so a huge column with very few unique values will not take up a lot of space. And this is used in writing the Parquet file format. And the gather is obviously it's sort of used everywhere in QDF because we try to materialize everything at our solutions at the very end and try to work with indices into the original data for as long as we can. We keep moving indices around, and in the end, we use gather to materialize the result. I have personally even used it outside of QDF. For example, the string gather is particularly useful if you have a bunch of discrete binary values you need to reorder. You just give it the order that you want and call gather on it. So these utilities are actually available to use. One of them, especially the hash map, has evolved into a library of its own, and it currently lives in a repository called QCollections. Jake is the maintainer to that. I think he's spoken here before. And the row operators and the gather are available in these two headers. So the row operators, I believe, is self-contained in the header. The gather, it's going to use you need the QDF lib as well. The fixed width, if you just want to do a fixed width gather, it's already available in Thrust, so no need to go to QDF for that. Now, let me bring you to the TCS solution to this. And the problem with the QDF solution, as I mentioned earlier, is that it only works on a small piece of data. It doesn't work on the entire 12 gigabyte file at a time. It certainly doesn't work on reading terabytes of tables at a time. So you need to use TCS to scale that across multiple GPUs, across multiple nodes. So the UI to TCS is SQL. So the SQL for our toy workload is quite simple. It's just a select, give me the city, the minimum temperature, the maximum temperature, the average temperature, group all of these by from this table and group all of them by the city. And the limit 10 is just so that the result doesn't flood my CLI output. But internally, it does go and operate on the entire database. So the running this, which internally uses the QDF group by, it runs in 8 seconds. Again, not too shabby. Compare this to the 13 seconds for the example solution. And this one doesn't have the advantage of being tailor-made, having tailor-made kernels for this particular problem. So it's using general purpose APIs for it. So what did TCS do internally? It converted the SQL into an execution plan. It figured out, okay, if I have this SQL, what does it translate to underneath to all of the QDF APIs that need to be called? It's going to then divide up all of those the execution plan into small tasks that can be run using QDF at a time. And each of those tasks will carry along with it an estimate of how much memory, how much output it's going to create based on historical data, how much operating bytes it needs based on historical data. And then it will refrain from launching each task until there's available memory on the GPU to run that task. And if there's a lot of memory available on the GPU, it's going to even call multiple QDF calls at the same time in order to saturate the compute. in the single GPU case that I just showed, that the 8-second one, the Theseus created 100 and took the 150, actually it's a 15 gigabyte file. It broke it up into 100 small tasks, each containing one CSV read and one group by. So the operating bytes needed for that group by are not a lot then. And then after that group by, hopefully the results were sufficiently small enough, because again, the number of cities are quite limited. You're definitely going from a 150 megabyte thing to at least a couple of megabytes thing. And then it's going to concatenate all of those results and do a group by again. But that's not where Theseus's true power lies. Its true power lies in multi-GPU execution, and it can do that by understanding how many GPUs does Theseus have right now. Let's say if it has 2 GPUs. In this case, it's going to assign each GPU 50 tasks to read those CSVs and then group by. And then it's going to hash partition those results. And it's going to hash partition so that it can share those with its neighbor GPUs. So in this case, once you partition this data set, these values will, the cities that these values will, these tables will contain will not be found in these tables. And the cities that will be found here are going to be found in the neighboring GPU. So obviously, Next is going to send those partitions over to its neighboring GPUs. Actually, not neighboring, but all of the GPUs available in the cluster. So it's going to create as many partitions as there are available GPUs. And then once each GPU receives the partition that it needs to work on, is the few subset of cities that it's going to get in the end, is going to concatenate it with the values it already has, concatenate again into a single table, and then run one more task to do a group by again. Now, these two tables on these two GPUs contain your actual result, and your CLI is going to give you back results from here. So that's how Theseus does it. And to recap, I went through the kind of problem that data analytics poses and why it makes sense to do it on GPU, because GPU is the only thing that can make it fast enough for you. No matter if you just have, even if you have unlimited money, then we went through a small toy workload to show how this pipeline would work by going through the GPU. We went through the example solution, the generalized solution, and then the cuDF solution. And then I explained the cuDF group by implementation, which uses a hash map, a row comparator, and a gather, which it also uses other things, but these are the things that I find important to talk about. And then we went over Theseus's solution and Theseus's group by implementation. That's it. That's my talk. Sorry, I didn't have an hour worth of things to talk about.
Not at all. And thank you so much. I really appreciate this talk. I did have a question, and folks, yeah, if you have any other questions about Devaret, like make sure to either raise your hand, I can let you on here, or just ask your question in lecture Q&A. So I think, like, for me, what's sort of unique about, like, when I think about data processing, it's like basically like the average size of a useful data set is much larger than the average size of a model. And so it's like kind of one of those situations where like you can quickly end up like with terabytes like worth of like data sets, but you rarely end up with terabytes large models. So I'm curious, like, how do the economics like work out, like especially as you go towards like a larger number of GPUs? How does this really work?
Economics in the sense?
Yeah, I mean, at some point, like, waiting is cheaper than making your results faster is really what I'm trying to say, like, as far as like time goes.
So I would like to take you to slide number, I don't remember. Wait. it was this slide, right? So notice there's also the dollar value of your cluster at the bottom. So if you have if you want to use the same number, if you have the same amount of money, you can either have your solution quick using GPUs or slow using CPUs, and that's what we are actually really competing against here. So the economics does kind of work out.
Oh, I see. And so all of these data sets that you're showing are like 100 TB.
Oh, yeah, no, actually each line is a particular scale. So that the bottom peach one is a 10 terabyte data set using 2 GPUs, 4 GPUs, 6, 8, 10.
Oh, I
sorry,
see.
2 nodes, 4 nodes, 8 nodes, and go on, so on and so forth. You might also see that the thesis can do 30 terabytes of compute using less money, less resources in the same similar-ish amount of time that Spark does 10 terabytes with a much more money.
Got it. So apologies if you covered this already, but like like I'm sort of curious, like how would joins work in this regime?
Yeah. So joins are actually much more complicated, and I didn't want to cover them because it wouldn't fit. But yeah, so joins also sort of use a lot of first making small pieces of stuff and then keeping hash tables around and stuff like that. So you doing hash partitions, sharing the partitions to which you think belong to a different GPU or to a different node, so sharing it to that one, and that guy gets to do its join. This is equality join that I'm talking about. Inequality joins are a whole different beast. And I'm not qualified to talk about them because I haven't worked on them so much.
So I guess like my last question was like I really like that you mentioned the collections library, because I did notice that like a lot of educational content on kernels just don't include data structures in CUDA, like just include raw kernels. So like in your work, have you noticed like certain data structures coming up like over and over again? I think like the hash map is sort of like a very obvious one for your kind of work. I'm curious in other
right.
uses outside of data processing, if you've seen data structures pop up over and over again.
So the co-collections one is interesting because I did want to share an anecdote of this one time I was making. cuDF also has a Parquet writer, and just to give brief context, Parquet is a binary format. So unlike CSV, you can't read it just from opening the file, but due to it being binary, it can do a lot of good things, like it can shrink, it can do compression, it can keep data in small chunks so that when you only need a small amount of it, you know exactly where to look for it in the file and stuff. And Parquet uses dictionary encoding as one of the ways to reduce file size. So the cuDF Parquet writer used to have a kernel that was doing dictionary encoding, and that kernel had a hash map implemented in the shared memory of that kernel. And to do that, there was a lot of CUDA ninja level hackery involved. I wasn't the person who did this. There was a much more senior person who wrote that kernel, and using there was a request to the cuDF team to as a reason of an assumption for that hash map was that the maximum amount of unique data can only be 16-bit worth of integers, so like 64K unique keys. But the customer came with a request for 24-bit, so 17-bit all the way up to 24-bit, because they had the kind of data that had more cardinality than just 16, but they still wanted to save space. And so I just ripped out the existing hand-tuned kernel with shuffles and whatnot, with very little amount of data going to the disk to the device memory and trying to keep things in shared and local as much as possible. I ripped that all out and replaced it with 4 separate kernels, all made using Koo collections. And it turned out the Koo collections one was not slower. It wasn't much faster either. It was the same amount of time. But using Koo collections, I could basically just tune 2 values, and suddenly my hash map that only worked for 16 bits now worked for 17, 18, all the way up to 24. So I became a big fan of co-collection style, reusable data structures like that.
Yeah, I really like that. Like basically the availability of better abstractions let you get away with like writing very competitive kernels with people that are like maybe the world's greatest at something, and you can do something really fast.
I would consider that engineer to be really great. Like I could not even comprehend that kernel, and yet by using something written by engineers much more smarter than me, I was able to reuse. I was just able to write a better solution. So, and that engineer actually is, I think you've met him, Jay Kenstad.
Yeah, that's
no, not the author of the super complicated kernel, the author of Koo collections.
Oh, got it. Okay. So actually, I want to make sure we get to the audience questions as well. So Jerry's asking, so how is Dask QDF, which works for multiple GPUs, different from QDF and TCS? Also, how is the performance difference between Dask QDF and TCS? Okay, so the Dask and Theseus have similar goals, which is to scale QDF computation. And Dask is what is used by NVIDIA as a solution to scale up QDF. I'm not sure if I'm qualified to officially state how much faster or slower Theseus is compared to Dask, but from what I've heard, it's quite fast. And it comes down to the fact that when you are dealing with QDF, you're dealing with Python APIs, and there's a bunch of time wasted with them. Whereas Theseus actually doesn't. Excuse me. Whereas Theseus doesn't use QDF, it uses it straight calls into libQDF. So just by removing some inefficiencies, it's able to get faster. All right, and then the second question from Kishimo, it's like they're prefacing this by saying this is kind of a vague question, but what kind of use cases does this new field find today? What kind of work is the users of these libraries doing? Yeah, so basically more talking about like the kind of applications, I guess, of people that are leveraging your work. For QDF, I can't really say how many people use it in how many different ways, but I just think that it's marketed as a faster pandas. And I think we have received a whole lot of questions from employees of companies as well as individuals trying to learn data analytics, just trying to make their pandas code go faster. So I think QDF enjoys a lot of visibility and usage across the data science community. Theseus is a proprietary product, and it's meant for companies which have data that truly is large, like in the terabytes of scale. So I'm not going to disclose the clients we have until I ask my manager. That makes sense. So another question is like, have you heard of the Rapids Accelerator for Apache Spark? Yeah. So I actually, as part of the QDF team, I was involved with the Rapids Spark team as well. Wait, what's the question? There is no question. It's more, have you heard of it? I guess you. Yeah. Actually, I worked with the Rapids Spark engineers, and they had quite many requests from QDF, pre-feature requests, which I did. So Kashimo again is asking, like, have you ever found yourself needing to like write SAS to optimize your code?
Uh,
I guess the question is more
no.
generally about writing low-level stuff like
No,
PTX.
no, and I can even count on my two hands the number of time I have used NCU at NVIDIA, and I attribute it to the brilliant tools that were made by the folks at NVIDIA as well as my colleagues at QDF, because a lot of the time, if I wanted to write a new kernel, I would just find if I just use a fancy iterator with Theseus, this would just go faster. Fancy iterator with Thrust, it would just go faster. So most of the time, my job, if even if I wanted to write a kernel, I would find a cub utility or any sort of utility available already. So even for that, the dictionary encoding for Writer thing, I only opened up NCU to see where exactly is a lot of compute happening, and if a certain kernel, like either the initialization kernel or the collection kernel, needed to be given more parallelism or something. But I hadn't had to go into SAS.
So it's interesting though, because like I've heard this feedback from like a few NVIDIA people, and it's interesting because people outside of NVIDIA are very much like, no, like you need to write the PTX. And then people that have worked at NVIDIA are like, hey guys, like, the abstractions are good, like learn how to use them. And I think you're sort of describing like Cub, Thrust, Q collections as libraries that feel like it's really, maybe worth a day of your time to sort of go through the docs and see what's available and like us together.
Yeah, definitely.
Yeah. So
there's also, I think, libq++, which was really helpful. I because I struggled with looking for things like I even here at Thesis, I wanted to use a barrier, and I found that there was just a very C++ ish barrier available already in libq++. So yeah, abstractions is the way to go, at least for data analytics.
okay, I think that's awesome. Like I think then we might end up thinking in future lectures about like having sessions on those like respective libraries, or like maybe like even more of like a live coding session with those libraries. So thank you, Dev. Like this was a fantastic talk. Like I personally learned a lot. So please make sure to, give a round of applause to Dev for coming in and giving us this talk. I think it's like one of the most different talks we've had as well, just like topics, because we tend to mostly attract people that purely work in machine learning. So this was like, I think, like thinking about a different use case. So next week we have a lot of sessions. By the way, we actually have on Thursday there's a CUDA optimization workshop happening in Chip Huiyan's like ML Ops Discord. So Chip was actually the person who introduced me to Dave, and so this is how all this started. But that's going to be a 3-hour workshop on Thursday, and it's covering, like I'm going to give a talk. Phil Tillett from OpenAI is giving a talk. We have some Mojo guys and some NVIDIA guys giving a talk. So my understanding is that a lot of the talks are going to be introductory. So if you're interested, I think it's going to be like a great series. On Friday, we have Izzat Haj, who's one of the co-authors of the PMPP book, who's going to come talk to us about like the scan operation. And then Saturday, we're gonna also have Jake and Georgie from the CUDA C++ team gonna talk to us about like advanced tricks to make scan and go fast using CUDA C++. So a whole bunch of talks. So if you want a CUDA mode, you can CUDA mode pretty hard next week. And thank you so much again, Dave, for your time, and thank you everyone, and see everyone next week.